Hi everyone, I'm Brad. So what we did is we applied system factorial technology, which is a methodology that we use in humans to detect what the architecture is of a specific cognitive process. So we applied it to a neural network to see if it could be used. So quick disclaimer before I begin. Unfortunately, Christophe Tremblay can't be here. He is the one who did all of the computational aspect of it, where it was to see how we could adapt system factorial technology to a neural network. So if you do have any questions on the code or anything at all, please feel free to shoot me an email and I'll make sure that he gets back to you. So, what's an SFT? The inability to look inside the brain has really frustrated researchers, which is why it came about. So it's a series of manipulations of the data and of the stimuli that allows for a 2x2 factorial design, which creates a specific curve for each type of architecture. So the 5 types of architecture that I can detect is serial self-terminating, serial exhaustive, parallel self-terminating, parallel exhaustive, and coactive. And it's almost magic the way it works. It's really, really cool, where we take a really simple part of the cognitive process, we dumb it down, so everything else is held as constant, and we just focus on that, and we vary stimuli according to it. I'll get back to it later. It's complicated to give in 30 seconds here. So each architecture, in the end, has a specific curve associated to it. So after you've done all the manipulations of the data, you should get a curve. So it's just a simple matching test, where if you have a straight line, the cognitive process that you're measuring is serial self-terminating. So what about the categories that don't necessarily, what about the architectures that don't fit these categories? And one of them is the bidirectional associative memory, which was spoken about yesterday by Melissa. So it's parallel units that iterate over themselves. So it has a parallel component, it has a serial component, which is the noise, it gets added up, and it has an iterative component, which isn't touched at all by SFT. So what would happen? Will we get a new curve? Are we going to get a completely messed up thing? Are we going to get a curve that's the same thing as this 5 that we have? So to show that it is in fact parallel, because we built it ourselves, we changed the input size. So if you change the input size, there should be no effect if it's in parallel, since all the pixels are basically checked at once. And if it's in serial, then all the pixels need to be checked one by one, so the time would be it would take a lot of iteration before it would balance out. So as you can see, nothing changes except for the frequency. And so the stimuli we use is 24 by 24 pixels of random input. Then we would pixel flip 10% if it was in a low condition, and if it was in a high condition, we wouldn't do it. So those are the 4 conditions that we get for the SFT methodology. And the SFT method is basically you gather the iterations, in this case, for all 4 of the conditions. We get the mean for all the conditions, then we measure the mean interaction contrast, which if the MIC is equal to 0, it's serial. If it's not equal to 0, it's not serial, so it can be parallel or coactive. After that, we transform the data distributions into survival curves. We measure the SIC, which is how we get the curves that I showed you earlier. So you just measure that formula on each instance in time between all 4 conditions, and then you just compare it to the theoretical curves, and whatever you get is, that's the architecture behind it. So you got the poster.